All right, so today we're going to look at the stress tensor again, but we're going to see that we can write it as two components. So the stress deviator tensor. Okay, so over here what we say is that the stress tensor so sigma Rj can be expressed as the sum of two other tensors. Okay, so the sigma ij here could be equal to S ij plus sigma sub naught delta ij. And I will specify now what is each one. Where the term over here, sigma sub naught delta ij, is the hydrostatic stress tensor. Okay, so what is the physical meaning? So let me just say that tends to change the volume of the stress body. Okay, and here the sigma sub naught is equal to the sigma sub naught, let's say II over 3, which basically means sigma 1 plus sigma 2 plus sigma 3 divided by 3. So this, when you put it into the matrix method, into the matrix form, would be equal to what? Sigma, not here, 0, 0. All right. And this one sometimes in some textbook they put as minus P, and they call this the mean normal pressure. If you are, maybe this might sound familiar, it's not that much about solids. This shows up a lot more about when you do fluids. For example, when you look at the mean stress given by water on top of a plate, you always look at the hydrostatic pressure, no? Okay, in multiple directions. So now the other term is what? Is the Sij, and this Sij term is the deviatoric stress tensor which tends to distort the stress body. So for instance, this is important one now for structures, no? For normal solid mechanics. Okay? Okay, so from above equation, which is this one here, we have that sigma ij equal to Sij plus sigma sub naught delta ij. So from here we can get that Sij will just be equal to sigma ij minus sigma sub naught delta ij. Or we could just write this as sigma ij. What is sigma sub naught? Minus maybe here I should use a different index because it doesn't matter over 3. Delta ij. I'm just using this notation here, no, for the sigma sub naught. That's what I'm doing. Okay, so what's important here now is to rewrite this equation in matrix form so we can observe something or notice something. So patient 7. Or in matrix form. What do we have? So S11, S12, S13, S21, S22, S23, S31, S32, S33. Equal to what? To the sigma ij, okay? Which basically is all those values again. Sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33, minus this term here, delta ij, will just give you the terms on the diagonals. Okay, so I'm not going to write the one on the left-hand side, it's long, but what's important here to notice is what? Is that we're going to have here sigma 11 minus sigma naught, sigma 1, sigma 1, sigma 22 minus sigma naught, sigma 12, sigma 2, sigma 13, sigma 23, sigma 33 minus sigma naught. So, what can you say about this equation? What does that look like? When you divide this one, that looks like solving the eigenvalue, eigenvector problem, no? Yeah? So that's why I wrote it under that form. So the above equation is similar to the eigenvalue eigenvector problem. Okay? So solving the eigenvalue eigenvector problem, what we're gonna have? Determinant of the sigma ij minus this is the same thing as this equation here, no? But in index notation, this is equal to 0. So probably the derivation, I might leave it as a homework, but if you solve this problem, when you write down the determinant equation, you obtain the characteristic equation, no? Okay, so this will give you the characteristic equation that is minus lambda to the cube plus J1 lambda what did I put this? Minus J2 lambda. Is it a square here plus J3? I may forget a square here. I'm going to check. But I will go check now. So where lambda here is the same thing as the S vector. We have that J1. So this is the characteristic equation. So I'm pretty sure here, I don't have it on my notes, but I'm pretty sure I forgot to put a 2 here. Right? Otherwise it makes no sense. Okay, so in this equation you have that black would be easier, that J1 is just equal to the SKK which is 0, which means this means state of pure shear. The variable or the constant J2 would be equal to 1/2 Sij Sji, which in matrix form is the same thing as doing 1/2 of the trace of S squared. So basically means you just take 1/2 of the diagonal terms. Okay, and here there is some small derivation, but I think I asked you to do that in a homework. This is equal to 1/2, obviously, of S1 squared plus, or S1 squared plus S2 squared plus S3 squared, which is equal to 1/6 of sigma 11 minus sigma 22 squared plus sigma 22 minus sigma 33 squared plus sigma 33 minus sigma 11 squared plus sigma 1, 2 square plus sigma 2, 3 square plus sigma 3, 1 square. Okay, this is equal. I'm just going to stop here. I have like 3 more lines, but I'm going to keep it here. This is 1/6 of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, so here be careful, guys, because what is the difference between the 1, 2, 1, 1 and then 1, 2, 3? This will be the principal stresses, no? On the principal directions, it will be the one on within the stress matrix. So maybe you can see more or less how does that looks like this time over here. Does that then kind of look familiar for stresses? No, no. Okay, we'll find out. But again, we have J1, J2. I still need to define J3, and then we can see. And J3. So J3 over here is defined as the determinant of Sij that gives you to be equal to 1/3 of Sij Sjk, be careful here, Ski, which ends up being 1/3 of S1 cube plus S2 cube plus S3 cube. I think there's a homework, you need to prove all this stuff. Okay, and we can leave it here, okay? 2 more lines for to put into matrix form and so on, but I think we can leave it like that. Okay, so let me write down over here a quantity, and this is why I'm doing all this stuff. A quantity called von Mises stresses is commonly used in solid mechanics and is defined as sigma von Mises equal to the square root of 3J2. This is too complicated now, but I'm going to put it, which suggests that yielding of a ductile material begins when the second deviatoric tensor J2 reaches a critical value. So let's see if I was able to write this one. So that will give us what? Von Mises square would be equal to what? 3J2 which should be equal to what? 1/2. I don't know if I'm gonna space. I'm copying here this equation here. All right. Okay, this one over here. So will be 1/2 of sigma 1,1 minus sigma 2,2 square plus sigma 2,2 minus sigma 3,3 square plus sigma 3,3 minus sigma 1,1 square plus 6 sigma 1,2 square plus sigma 2,3 square plus sigma 3,1 square or in function of the other ones will be 1/2 of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, and it can be proved, but this one, I'm not gonna do it, that is equal to 3/2 Sij Sij. Okay, so again, this is not that important here. I mean, it is important from the conceptual point of view, but really what you need to know over here is that from a practical point of view is that so far we have studied two different stresses, and that's why I do both of them. First one we did were the principal stresses, okay? From the principal stresses, you can define the von Mises stresses, all right? So my question is, which is more important than the derivation, for what type of material do you use von Mises stresses, and for what type of material do you use principal stresses? The answer basically is here for von Mises. What type of material? For what type of material is the von Mises criteria generally used? For ductile material. Ductile material means that are ones that can deform, no? Aluminum, steel, stretch, no? Okay. What about the principal stresses? Principal stresses are generally used for brittle materials. So for example, if you're going to study composite, which one should be better, the von Mises or the principal stresses? Principal stresses, okay? If you study a glass, something that is brittle, generally you will go for principal stresses, but if you study something that is ductile, you will study with von Mises, okay? And that's why sometimes maybe if you don't see that you have this ratio here of 3.5, maybe if you do civil engineering, you find out that what is for them the maximum ultimate stress that they put into the design when they do the structure is 1.5. That ends up being 3.5, no? Okay? It's because it's based on von Mises. Because generally in civil engineering, what do they use? Ductile materials. Okay? The reason is over here, it's derived over here. Okay? But I think it's more important here to see this graphically, even though the figure might be a bit difficult to do. I mean, it's not really that difficult, but let me do it on a different page. I think that figure is important, okay? Personally, I think it's the best explanation. of the different criteria. So let's say you have the two in 2D. So in 2D, we're just going to look at the sigma 2 and the sigma 1. Okay? So let's see how I'm going to do this. So if you do the principal stresses, this is basically what you're doing. If your point is within the square is safe, if it's outside the square is not safe. Okay? All right? Now, the von Mises, it's a little bit more difficult, but it's like it goes from this point here, then it goes through this point here, it goes through this point here, then this one, then this one, and this one. So it's kind of an ellipse that goes like this. So go that one. Yeah, so that one. We're gonna do this. Now I start turning this way, goes here. So it's something like that, okay? Johnny is a bit bigger, but this will be the von Mises criteria, okay? And then there's another one, but this one is generally more used in, for machine design, okay? Is the Tresca stress criteria. Which is what? Sigma of Tresca is equal to 1/2 sigma 1 minus sigma 3. Okay? And this one is more like, let's see how. We go from here. So it's like tangent to this point here. It's difficult to sketch. It's tangent to all these curves here. I don't know how good it's going to be. So, because really, this is really an ellipse. You see, I'm not doing a good job here. This is from here, 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 tangent. Is tangent to everything, basically. I should also be tangent to this one here. So, I did not do a good job, but do you see what I want to say over here? It's tangent to all these curves here. So basically, what it means is that you see that if you do the figure between the different stresses, what is the assumption that can happen over there, no? Okay, for the deformations. All right, so let's do an example. Wait for a minute. All right, example. So we have here the stress matrix representation at a point P is given by sigma ij will be equal to 29, 0, 0, negative 26, 6, 6, 9, 0, and 0. Okay, and the question is to determine the hydrostatic and deviatoric components or determine the hydrostatic, comma, deviatory components and principal stress values. Okay, so over here we just study what? We know that by definition, the stress tensor, you can rewrite it into two components, no? The deviatoric or deviator stress plus the hydrostatic component of Ij. So here, this is very easy to do this one. This one is equal to what? This one is just equal to the terms of the diagonal, no? So we put the definition, sigma I over 3. So I want to save some time. This is equal to 29 minus 26 plus 9 divided by 3, which is going to give you what? So this is 29 stress 3, 9 plus 3, 12. 12 divided by 3 is 4. Okay, and this should be for the units for KSI. So now we know that in order to solve for Sij, we need to go and solve the eigenvalue problem, no? Okay, so let's just do that. Page 80. Okay, and we just saw that Sij, the stress tensor, deviatoric stress tensor, equal to sigma Ij minus the hydrostatic pressure of delta Ij, which is equivalent to solving the eigenvector problem. But let's just rewrite it. So this will be equal to what? So let's see. What was that matrix over here? So we have 29, 0, 0, no? 29, 0, 0, 0 minus 26, 6, 0, 6, 9, minus the diagonal that needs to be all 4s. So 4. So this is going to give us that Sij will be equal to what? 29 minus 4, 25. Then we're going to get 0 here, 0 here, 0, negative 30 minus 26 minus 4 is 0.
No, it's not 6.
This would be 6, sorry. Then we have 0 here, 6 here, and then at the end we have 9 minus 4, 5. Okay? So now we need to solve the eigenvalue problem for this matrix over here. So the next thing we need to do is solve eigenvalue problem for Sij. Okay, so what is the eigenvalue problem? Remember, it's Sij minus a quantity over the diagonal, identity matrix. But remember, conceptually, what is the eigenvalue problem is that you are trying to solve to know what is the principal directions for the stresses, no? You're not going to know the magnitude, but you're going to know the general direction, no? Okay, so that's what we're solving here. So this will give you what? This will give you the problem of, will be 25 minus lambda. 0, 0. Try to correct this one. Now will be, the middle will be minus 30 minus lambda, 0, 6. And then 5 minus lambda, 6, 0. Okay, the next step is what? To solve the determinant of this equation. So this is equal to 0. We need to solve the determinant of this equation to find the characteristic equation. So solving the determinant of Sij minus delta I equal to 0. This would be equal to what? So it would be equal to 25 minus lambda times this one minus this one times this one, no? So of minus 30 minus lambda times 5 minus lambda minus 6 times 6. And the other two will be equal to 0, no? 0 and 0, all right? So this is going to give us 25 minus lambda. Oh, okay, I'm going to do the middle step. That way, minus 150 plus 30 lambda. So this is the 5 times 30 plus 30 lambda minus 5 lambda plus lambda square minus 36. This will give you, this is equal to 25 minus lambda times the quadratic equation, lambda square plus 25 lambda, 30 minus 5, minus 186. And this must be equal to 0. No need to factor out because what we're trying to find is the roots, no? So here we go, we know that already one root is 25. Then we need to find the other two roots for this one. So this is the characteristic So the 3 eigenvalues corresponding to principal stress values are what? Would be, so generally you go from, okay, here I did, all right, so if we do, okay, I have a different order on the notes, but it's fine. Delta 1 equal to 6, delta 2 equal to 25, that doesn't matter, delta 3 equal to -31. So this 6 minus 31 would be the roots of this polynomial here, no? Okay? But now what happens is that this will be equivalent to what? This will be the maximum value, S1. This will be the maximum value. S3, which would be the S3, will be the minimum value. And this will be the components of the stress 2. Okay, so basically we found the value of the deviatoric, and this will be the value of the principal stresses, no? Which correspond to the eigenvalue. Okay, now for today, I'm just planning on doing one more thing. I want to start the next big package. So just to show you that what we have covered so far is the most traditional stress models, the ones that I personally teach when I teach all my classes, and the one that show up in almost every single textbook, okay? But that there is other definition for stresses, okay? So one of them here is the Lame's stress ellipsoid. And you will see that this guy, Lame, was very famous. When you go to stresses, he's the one that derived all those matrices. But basically, the only thing I'm trying to show is that this figure here shows the most traditional stresses models, but there are others, no? Okay, that you can use. All right, so for Lame, let's say let the principal axis of the stress tensor be chosen as the coordinate axis is repetitive, but x1, x2, x3. Okay, actually this is extremely important what we're doing now, okay? So be careful, because this is not another model, this is the definition of the Lame stress. So sigma Ij will be again just the components on the principal directions. Okay, so this is what we did before, really. I'm not redoing anything new. So it will be Ti of the normal vector n is equal to the sigma ij and j, which basically, if you expand it, is just equal to sigma 1 and 1, sigma 2 and 2, sigma 3 and 3, which is equal to the stress vector T1 and T2 and T3, and you don't need the n if you don't want, okay? And since n hat is a unit vector, n1 square plus n2 square plus n3 square will be equal to T1. I don't want to put the n, it's going to be too much. I'm going to forget about the n here, T1 square over, but this is, should be the T should be the same as this one. Sigma 1 square plus T2 square sigma 2 square plus T3 square over sigma 3 square equal to 1. So you can notice that this is the equation of an ellipsoid okay, centered at the origin. So if we do this on the figure, x1, x2, x3, this. And if we look from the origin here, this could be your stress tensor T, N, and let's say this could be your unit vector here, N. Okay, so I'm gonna stop here the video, but we're gonna keep talking about this.